We are starting a new unit called Graph Theory that's going to help us get into what we call networking. And so eventually out of this will come a lot of different ways that we can look at to provide algorithms for automated processes, etc. So let's take a look at this first section. Let's define a couple terms. I do have to warn you, this particular lesson is a lot of definitions. All right, so you want to make sure you hold on to this. Well, let's first take a look at what we call a graph. And this doesn't look like the normal graphs that we were talking about on the X and Y axis. It consists of a finite set of points called vertices. And so those are these points right here. All right, so where you see these dots, those are our vertices. And then the line segments or curves called edges that start and end at vertices. An edge that starts and ends at the same vertex is called a loop. So you can see there's one right here. Down here, we have a vertex, and then it takes that edge and comes right back to that vertex. So that's an example of a loop. Let's see here. Two or more distinct edges with the same set of endpoints are said to be parallel. Okay, so here's the weird part. This one and this one are considered parallel, and the reason is because they both start at A and they both end at D. Do not think about your geometric parallel, where two lines are the same slope and that they never meet. That's not true of graph theory. So when we talk about parallel, it just means that there's two edges going from the same vertex from one to another. All right, so identify the previous definitions on the graph below. Okay, so anywhere that we want here, we're going to go ahead and let's note that this is a loop. Okay, and here we have parallel edges. All these little points here are single vertex. Many of them is called a vertices. And then be very careful when they cross. This is not a vertex. Okay. When you look at edges, you can call it whichever way. You can call it AD or you can call it DA. It really depends on what the makeup of the graph is and what direction you're taking your path. All right. So let's take a look at some more information here. In a graph, the important information in which vertices are connected by edges, two graphs are equivalent. Equivalent. So not equal, but essentially have the same information. If they have the same number of vertices connected to each other in the same way, those are what's equivalent. The placement of the vertices and the shapes of the edge are unimportant, so they don't have to look alike, which is strange. When we think of equivalency, we think of something that is fairly equal to or same as, and these are not going to be the same. But what we have are a couple features, right? Let's look at this first example. Are the following graphs equivalent? Explain. If so, can you draw a third one? Okay, so pause this for just a second. See if you can detect if these are the same. All right, let's take a look. This one here on the left goes from A to B to C to D. I could also say that it goes from D to C to B to A. It doesn't matter, but that is my order. On this one, it goes from A to B to C to D. Or we could say that it goes from D to C to B to A. So because both of these have A, B, C, D, and they're only connected in that way, these are going to be the same. So yes, because they have the same vertices, meaning A, B, C, D, and the edges between the vertices connect in the same way. Okay, so if this had been, if we had had, let's say, a line from D to B, that would not be the same unless we also had a line from B to D on this one, right? So we have to kind of look at some of those things. So can you draw a third one? Go ahead and pause this and see if you can draw a third one. Okay, let's take a look at some other options. I can make a big old U shape, right? And as long as I have A, B, C, D, that would be an equivalent graph. It doesn't look anything like the other graphs that we have, but that's okay. I could have one that looks like A, B, C, D. So kind of like a trapezoid, right? These are also equivalent because I have the same vertices, A, B, C, D, and they're all connected in the same way. All right, consider the drawings below. Can you label the second picture so that it is equivalent to the first? Okay, so what we want to do is typically you've got to start somewhere, right? So I have A over here. So I'm going to go ahead and label this A. And then I look to see A goes to E, and A also goes to B. A goes to E, and A goes to B. So what I'm going to do, A goes to B, and A goes to E. All right, so now let's look at B. From B, I came from A to B, and I went from B to C. So I'm coming from A, and then I'm going to C. All right, so I think I'm going to see a path here. So came from B to C, now I'm going from C to D. So going from C to D, that's going to be D. And let's just verify here, going from C to D, and then D goes to E, and then E goes back to A. So C goes to D, D goes to E, E goes back to A. All right, so that's how you would draw or label, I guess, an equivalent graph so that it looks the same. All right, so let's take a look at these two. Okay, think about these two. What's happening? B, what I like to do is look at where the complicated pieces are, right? So A only has two lines coming from it. It has this line and it has this line. B has 3 lines. D has 3 lines. C has 3 lines. And E has 3 lines. So I know that my C and E and my B and D are connected together. I know my D and E are connected together. And C and D and B and E are together. Now when I look at this, I can kind of see that X right here that we have right here. So to me, that looks like it's pretty equivalent that way. So it almost looks like a distorted version of this triangle that's kind of lying on its side. All right, so I'm going to label it A, C, E, D, B, and then I can always check myself, right? So B goes to E, A, and D. B goes to A, D, and E. So we're good on that. C goes to D, A, and E. C goes to D, A, and E. We're good? A goes to B and C. A goes to B and C. And then D goes to B, C, and E. D goes to B, C, and E. And then I can check on E. E goes to C, B, and D. C, B, and D. So it looks like we've got a pretty equivalent graph there. Okay? All right, let's take a look at some of these other situations. where these things are representative of specific examples. Okay. All right. There are many situations where we can represent or model using graphs. We will look at several of these situations now. Example 4. In the early 1700s, the cities of Königsberg, Germany, was located on both banks and 2 islands of the Pregel River. The picture below shows the town's sections were connected by 7 bridges. Draw a graph that models the layout of Königsberg. Use vertices to represent the land masses and edges to represent the bridges. Okay, so here's our bridges that we have. So we've got all these bridges. Then we would have a vertex here, and I guess a vertex here, sort of, right? And this would be another landmass. That would be a vertex. And then this would be its own landmass. So that's a vertex. Alrighty, so here we've got a couple things. We have almost everything, or at least 5 things really, connecting to this thing called the island, and things go out from it. All right, so there's 5 things that come out from that island. So I'm going to go ahead and put down a dot, and I'm going to call it A. And I have 5 things coming out from that island. Now, both of them, let's take a look up here. This is one landmass. And so I have these 2 bridges connecting to that one landmass. So these are actually going to connect. Let's call this B. So these are going to connect to B. Okay, I'll clean this up a little bit so it looks a little better. Okay, so these are going to connect to B. And of course, I bet you can guess when we're looking at the bottom bank, these 2 are going to connect to something. Let's just call it C. Okay, so we can just go in order. You don't have to go A, B, C, D, right? You can start with whatever one you want, but typically we go consecutively. All right, and then we have this island over here. It's its own vertices. So we have 1, 2, 3, 4. So I'm going to put that over here. That's D. Okay. So we know that A is going to be connected to D. So I'm going to connect A to D. This is starting to look like a pretty flower. We also know that C is connected to D right there. So C is also connected to D. And you could do a straight line. You could do a curve. It doesn't really matter. It's as long as you have the connections correct. And then I see that there is a connection, right? We called this D. We called this A. We called this B. And we called this C. So we had 2 lines from A to C. We had 2 lines from A to B. We had a connection to D. And then I got to connect D to B. I think that's the last connection for me. Okay. So that, believe it or not, would be an example of using edges and vertices to actually represent a landmass. All right. The map below shows the New England states. Draw a graph that models which New England states share a common border. Use vertices to represent the states and edges to represent common borders. All right, so we can do whatever you want as far as labeling. We can label them A, B, C, D, A, B, C, D, E. We can label them with their abbreviations, their state abbreviations. That might be a way to go. Okay, so we have, I'm just going to go ahead and put them out. So we have Maine, we have New Hampshire, we have Vermont, we have Massachusetts, we have Connecticut, and we have Rhode Island. Okay, so those are our vertices. So imagine these as huge dots, right? Okay, so let's take a look at what's happening with Maine. Maine touches only New Hampshire. It doesn't look, there's a little bit of a space there, so it doesn't touch that. So Maine is connected to New Hampshire only. So Maine and New Hampshire are going to be connected with an edge. Once I get to New Hampshire, it's connected to several. So it's connected to Vermont. So let's draw a connection to Vermont. So that's connected. I also have a connection to Massachusetts. I'm going to, oh, careful. See what I just did? I just continued on. I want to connect that New Hampshire with Massachusetts. And I think that's it. It's just connected with that. All right, so Vermont now is connected to New Hampshire, which we've got that. And then it's also connected to Massachusetts. So, whew, all right, we're good on that. And then we have Massachusetts, which is connected to New Hampshire and Vermont. We already got that. But below it, it's also connected to Connecticut and Rhode Island. So it's also connected to Connecticut and Rhode Island. And then Connecticut is also connected to Rhode Island. So that's a way to show that we've got all of those things connected. There's different ways to do it. Your graph may look different, but the bottom line is we've got all of our pathways done the way that we need to. All right, example 6, we have a floor plan of a 4-room house as shown below. The rooms are labeled A, B, C, and D. The outside of the house is labeled E. The openings represent doors. Draw a graph that models the connection relationship in the floor plan. Use vertices to represent the rooms and the outside and edges to represent the connecting rooms. Okay, so here's what I'm going to do on this one. Because we have, right, all these things connect to the outside, because so many of them connect to the outside, I am going to go ahead and put E in the center, okay? I'm going to put E in the center. And then I'm just going to kind of put everything. Now I could geographically put it in the order that we see it, but I can kind of tell that all of these are going to be connected to the outside. And so it makes more sense to me to have it connected that way. All right, let's take a look at A. So A has several things going on. It's connected to room B. So we're going to have a connection right here. It's also connected to room C. So we're going to have a connection there. We also have there's one exit and there's 2 exits. So there's 2 ways to get to E. So A has 2 paths to get to E. So we have a loop there. Make sense? All right. Now let's look at B. Okay. B is connected to A. We already have that. It's also connected to D. So I'm going to actually erase this E and put it closer. All right. So we've got B and D connected. And then I have B goes to the outside only one place. So I'm going to connect that one place. And then I look at D. D is connected to B, which I already have. And then D has the ability to go outside. So that's going to go to E. And then it also is connected to C. So it also has a connection here to C. And then C is connected to A and B, and we've got that. But C can go outside in 2 different ways. And so I'm going to have another loop here on, not a loop, excuse me, 2 parallel paths on C, from C to E. All right. So it might not look that way. If you wanted to do A, B, C, D, E, you can do that too, right? And then it looks more like the house, right? Where they're all connected. And then you have, right, two ways to get from A to E. You have two ways to get from C to E. You've got one way to get from B, and then you've got one way to get to D. So there's all different ways to do it.